All right, good morning. First thing I'm going to talk about today is linear dependence and linear combinations of vectors. So this is going to be a big deal for us. So linear dependence is for our situation, is a set of vectors are linear dependent if one of the vectors in the set can be defined as a linear combination of the other vectors. Okay, so that said, a linear combination of vectors is an expression involving scalar multiplication and the sum or difference of two or more vectors. Okay, are any three vectors, oops, I made a typo here, complanar? That's not right. Let's see if I can fix it here. I don't know if I can. It's supposed to say, obviously, coplanar. Oh my god. So, let's see here. Coplanar. Sorry. So, and the answer is if they are linearly dependent, yes. That said, they can't all be the same vector. So you can't have the same vector 3 times, and that won't be enough. But if any third one can be the combination of the first two, yes. So can the 3 vectors form a triangle by lengthening, shortening, or adding the vectors? Well, yeah, so let's say I have 3 vectors. Let's say I have, let me just get this right here. Let's say I have vector P. Hopefully I can do this without taking up all the room. And then I have vector R. Let's see, I'll put that there. And then I'll say I have vector D. So what I want you to try and imagine is, can we make like a little triangle out of these things? So, could I imagine vector P? I should have drawn this a little less perfect actually. So let's imagine I extend vector P, so I multiply it by some value that makes it a little bigger. And then I can copy vector R. I'm sorry, vector D is what I mean over here. So what this would mean here is that PD is equal to R. I should say P plus D is equal to R, right? So there's some value, I'll say here, I shouldn't say just PD. I should say there's some value, maybe M, times vector PD, so some scalar vector, and then plus some scalar vector times vector D, I'll say KD, such that it equals R. Does that kind of make sense? Maybe it does. So the other way to kind of think about it is, maybe I'll just do a new slide here and draw a different diagram. I have actually a little bit of another idea here to share with you guys. So I'm going to relabel this a little bit. So let's say I have vector here, then I have a vector here, and I have a vector here. And actually, let's call this point here P. I want some letters. So I'll call that S, R, and D again here. And so another way to kind of think about this is, there's such a way, a linear combination, so you can multiply by a scalar and add the vectors together, such that you can make the 0 vector. So I propose that some scalar M times vector PD plus some scalar K plus vector PR plus, let's see, I like to use rho here, but let's see, maybe I'll use L or something. L is a scalar times PS that equals the 0 vector. I haven't really talked about the 0 vector, but it must exist, right? Like, just like it exists in our number system, there must be a vector that has no change. So there. So we can also express this. So say we wanted to find vector PS in terms of the other vectors, right? So find PS in terms of PD and PR. Those would be the other two vectors, right? So, okay, so what we can do then is we can basically subtract MPD and KPR to the other side to get PS, right? So we could say that LPS, oops, is that right? LPS, where PS is the vector, is equal to, let's see, we'll say negative M times vector PD minus K times vector PR, right? And then of course we could divide everything by L. So we could say that vector PS is equal to negative M over L, that's just a scalar, times vector PD minus K over L times vector PR. So that can be true for any of the other vectors too. You can solve for PR, you can solve for PD. But what this is saying right here is that this expression right here is a linear combination of the other two vectors in this system. So PS can be expressed in terms of the other two vectors, where this negative M over L and this negative K over L, that's just a number, that's just a scalar. So this is just scalar multiplication, and in this case, subtraction. So I'm going to pause there for now.